Welcome to Virtual Pathfinder channel. This is a short video about artificial gravity. So why do we need this? The problem to solve is the many effects on human health caused by weightlessness in space. When spending extended periods of time in weightlessness, we rapidly lose bone density, muscle mass, and there are several other problems such as upper body fluid retention and weakening of the heart muscle. All those effects are related to the adaptations of the human body to an environment with no resistance from gravity. As the name indicates, artificial gravity is a way to mimic the effects of gravity. In Newton's mechanics, the force of gravity is defined by the formula F equals the gravitational constant multiplied by the mass of the first object and the mass of the second object divided by the square of the distance between them. The force of the gravity on the surface of Earth then becomes F equals the mass of an object multiplied by the gravitational constant times the mass of the Earth divided by the square of the radius of the Earth, and that is equal to m times little g, where little g is the gravitational constant multiplied by the mass of Earth divided by the square of the radius of Earth. In order to create a corresponding force using linear acceleration, Newton's second law of mechanics states that the force experienced by the moving object is F equals the mass times acceleration, and if that is set to be equal to mg, corresponds to saying that the acceleration is equal to g, which equals 9.81 meters per second squared. To achieve this situation, a spacecraft has to continuously accelerate at a rate of 1g. Then an astronaut standing on the back end of the rocket will experience a force which equals the gravity on the surface of Earth. The problem with this solution is that it's very energy consuming. From a practical perspective, with today's technology, that's not a feasible solution. Artificial gravity can instead be created using rotational movement, where a centrifugal force, which is a fictitious force, will mimic the effects of gravity in the direction away from the center of rotation. Assuming there is a constant angular velocity, omega, and that the astronaut stays at a constant distance from the center of rotation, the force experienced by the astronaut will be F equals m omega square r, where r is the distance from the center of rotation. If this is equal to the force of gravity on Earth, we have a situation resembling the gravity where F equals m omega squared r equals mg, which corresponds to omega squared r equals g. When standing inside a rotating barrel, this force will pull the body away from the center of rotation.